Hello everyone. Today I am going to explain you about the least square optimization algorithm for the low pass filters. Myself, Pranay Raj Mulpur. Okay. Let's quickly have a recap over the project. So, designing the low pass filter with a least square optimization to improve the filter's performance is the aim of our project. So least square optimization can be used in design of a low pass filter to determine the optimal filter coefficients that minimizes the difference between the filter's output and the desired frequency response. We should define the desired frequency response of a filter, which can be done using a mathematical function or by specifying a set of frequency points and their corresponding magnitudes. Then we should define the filter coefficients as a variables in a system of equations where the frequency response of the filter is one of the equations. Now we use the least square optimization algorithm to find the values of the filter coefficients that minimizes the sum of square differences between the filter's output and the desired frequency response. Now with the optimized coefficients, when we implement the filter, then it's possible to obtain a filter with a frequency response that closely matches the desired response, resulting in improved filtering performance. Now, what is a least square algorithm? So, the least square optimization algorithm is a mathematical technique used to find the best fitting curve for a set of data points. The basic idea behind this algorithm is to minimize the sum of square differences between the observed values and the predicted values. In other words, the algorithm finds the value parameters in a model that minimizes the sum of square differences between the predicted and actual values. This method is widely used in regression analysis, where the goal is to fit a model to a set of data points and use it to make predictions. There are several variations in the least square optimization algorithm, including ordinary least squares, weighted least squares, and nonlinear least squares. Overall, the least square optimization algorithm is a powerful tool for finding a best model for a set of data points. A low pass filter. No, let's know about what low pass filter. A low pass filter is an electronic device that allows signals with a frequency below a certain cutoff frequency to pass through it, while attenuating the signals with frequencies above that cutoff frequency. The main use of low pass filter is to remove high frequency noise or unwanted high frequency signals from a signal, allowing only the low frequency components of a signal pass through. Now this is the first order low pass filter, and here we are setting the cutoff frequency to 1 kilohertz with a transfer function of omega c by s plus omega c. Here we are taking omega c as a common, and here what we get left over with 1 by 1 plus s by omega c. So this is our original signal before we are passing it through the low pass filter. Now when this signal is passed through the low pass filter, the signal with the frequency below a certain cutoff frequency are passed through a low pass filter, while the signal with the frequency above that frequency got attenuated. So here what we are left with. So this is our original signal initially before passing it through the low pass filter. So when we pass this signal to the low pass filter, so this is what we got in the final as a final output. Now, significance of optimal coefficients while designing the low pass filter. So, impact on the performance of filter with the optimal frequency. So, what impact it is showing on the filter with these optimal frequencies. So, why we are using this least square algorithm for to find optimized filter frequencies, and we are giving these optimal frequencies to the low pass filter. So, why we are doing all this nonsense? Now, let's know about this. So the least square algorithm can have a significant impact on the performance of the low pass filter. So by optimizing the filter coefficients to minimize the difference between the filter's output and the desired frequency response. So here the algorithm can improve the performance of the filter in the several ways. Like first thing, so here improved frequency response, and next it reduces the passband ripple, and it also improves the stop band attenuation, and it also improves the stability of the low pass filter. Now, so the least square algorithm can help to improve the frequency response of the low pass filter by minimizing the differences between the actual frequency response of the filter and the desired frequency response. This can lead to a more accurate representation of a signal being filtered and improve signal to noise ratio. Next is a reduced passband ripple. So this algorithm can help to reduce the amount of ripple in the passband of the filter, which can improve the filter ability to attenuate the unwanted frequencies in the passband. Improve stopband attenuation. So this algorithm can also help to improve the attenuation of an unwanted frequencies in the stopband of a filter, which can improve the filter's ability to reject the unwanted signals. Improved stability. So this least square algorithm can help to improve the stability of the filter by ensuring that the filter coefficients are optimized for the desired frequency response. So this can help to prevent the issues such as filter oscillation or instability. So overall, the use of least square algorithm in the low pass filter can result in an improved filter performance, particularly in terms of frequency response, accuracy, uh, passband ripple, stopband attenuation, and filter stability. So these terms we are familiar with these things, right? So what is passband ripple? So passband ripple is it refers to the variation in the amplitude of filter's frequency response within the passband in the low pass filter. The passband is a range of frequencies that are allowed to pass the filter with a minimal attenuation. So stop band attenuation. So it refers to the amount of signal attenuation that the filter provides outside of its passband. So in a low pass filter, the stop band is a range of frequencies that are attenuated or blocked by the filter. So this stop band attenuation is a measure of filter's ability to reject or attenuate the frequencies outside its passband. And stability of a filter. So this refers to the ability of the filter to produce a bounded output for any bounded input you give over the intervals of time. So in other words, the stable filter will not exhibit any unstable or erratic behavior when processing an input signal, and output of the filter will remain within the reasonable range of values. In this case, in the case of low pass filter, stability is important to ensure that output signal is reliable and predictable and does not contain any unstable or oscillatory components. Unstable filters may produce output signals that are distorted or noisy, or may cause issues in downstream processing or analysis. So here this is how we are implementing the low first order low pass filter with the least square optimization. So this is the output when we implement it in the Python library using the NumPy as NP and Matplotlib libraries. So we are implementing the first order low pass filter code with by taking the optimal frequencies. Like here, see, here we are imputing the NumPy and Matplotlib libraries from the Python modules, and here we are defining the input signal. So this is our sampling frequency and this is our input signal frequency, and here we are defining the time period, and here we are giving the signal. No, here we are defining filter parameters. So this is our cutoff frequency and this is our cutoff frequency in radians per second, and here we are defining the order of the filter. Now we are going to define the filter coefficients using the least square optimization. So we are creating, so the basic idea behind this is to create the arrays of points, so which can reduce the difference between the squares of the predicted and the values which we are going to have, right? So these are the arrays of points. So the program will execute every point and checks whether which point is getting nearer to the predicted values by taking all the optimal frequencies from the arrays. So we are going to apply the filter to the input signal. So y is our output. So for this order of the array which we have already created, so we are finding the response of the filter. So once we have plotted every point, like once we have for every input x, we get some output y. So for this every point we calculate. So we collect all the ordered pairs x comma y, and using the matplotlib library from the Python. So we plot these all x comma y points, and here the red one which we get in this output response is our filtered signal, and the blue signals which we are which is behind this red signal is our input signal. So this is how the first order low pass filter is attenuating the remaining portion. I mean, in the stop band, whatever the frequencies are in the stop band, it's just attenuating it, and whatever the frequencies are in the pass band, it's just allowing them. And by allowing them, we are using the optimal frequencies, so that we are getting a frequency response which is closer to the desired frequency response which we want to get. Next, so here we implementation of first and second order LPF with least square optimization to observe the difference. So again, we are taking a sampling frequency of 100 Hz and input frequency we are taking 20 Hz. Cutoff frequency of first order we have taken 350 Hz, and the second order we have taken 400 Hz. So these cutoff frequencies doesn't make a matter. So here we are taking the second order frequency as a 400 hertz to just let us know the difference between these two. Like if you are taken 350 hertz, you will get the waves like you don't observe any difference between the first order and the second order low pass filter. So for that difference, I have taken some more different values, like slightly more than the first order filter. So same things, just how we have done before. We have imported the libraries, and then we have defined the input signal, and again we have defined the filter parameters. So here we are defining two filter parameters separately. So FC1 is for the first order filter and FC2 is for the second order filter. So everything is done. Next we are again creating an arrays. So for the least square optimization, so here we are having optimal filter coefficients, and then we are having a transfer function for the first order filter and the transfer function for the second order filter. So here see np dot, so this one is a dot product. So this does a dot product for the matrices, and this linolg is a library which imports the linear algebras, and this INV does the inverse of the matrices. So what we are doing here is, so first here we take here np dot x1 dot t into x1. So here we are doing a dot product for the x1 transpose with its x1. Okay, so then we are doing the inverse of this, and then again we are doing the dot product with the x1 transpose with the whatever the matrix we have obtained after implementing this. Then with the result whatever we got, so we're gonna make a dot product for the again with this matrix to the x matrix. So then we are going to obtain this h1, the transfer function. So you're going to get an array of h1, and in the second order, so we are doing the same thing, but we are taking the x2 here instead of x1. So we get separately two h1 and h2 matrices. Now we're going to apply these filters to the input signal. So we get our order pairs of x1 y1 and x2 y2 with a different value. So taking some x1 as a some input, and you get a y1. So taking x2 you get y2. So we are just arranging these ordered pairs x1 y1 x2 y2s, and we are plotting the graph. So this blue is the input signal, and this green one is our first order filter signal, and the second one is a second order filter signal. So this matplotlib library used to plot the ordered pairs whichever we got. So these responses will be uh, plotted by using this matplotlib library. So the difference in output being implementing a filter with and without least square optimization depends on several factors, including design specifications of the filter, the filter structure used, the optimization algorithm itself. In general, the use of least square optimization algorithm can result in a filter with a frequency response that closely matches with our desired response, which can improve the performance of the filter. So without optimization, the filter may not achieve the desired frequency response. So additionally, the use of optimization algorithm can help to reduce the complexity of the filter design process. So making it easier to design the filter with the complex frequencies response requirements. This can be especially beneficial in the cases where the filter design is constrained by factors such as hardware limitations, computational resources. However, it is important to note that use of an optimization algorithm may also increase in the computational complexity of the filter implementation. So though we are getting a good frequency response from that optimized filter, the drawback here is, so here we are doing more computational, so we are complex, we are complex, so the computations which we are doing becoming the complex. Okay, and also, so because of the computational complexity, the processing time to optimize the filter coefficients will also increase. So response for the input whichever we are giving, so we'll get somewhat delay here, so you'll get more time, so this increases the processing time and resource utilization. So for certain applications this is not preferable, where time matters and resource utilization matters. So in summary, the use of least square optimization algorithm can improve the performance of a filter and simplify the filter design process, but it may also increase the computational complexity of the filter implementation. However, as of now, we are concerned on the performance of the filter, so we use the least square optimization for having a better output. Okay, so this is how the difference between like this one, so this one is the filter's response with optimization, and this one is a filter response without optimization. So when we have plotted these two graphs separately by defining the function, so one we have taken directly and another one we have taken the optimal filter coefficients to have a optimized filter response. So this one is without optimization and this is with the optimization. So see here we can see the attenuation has been improved when compared with these two, and the ripples have been decreased, and the stability is also increased for this filter when you are using the optimization. But only drawback you with the optimization is it increases the computational complexity and resources. That's all. So now least square optimization, so this is what we are discussing about. So it's generally a part of least p algorithm, so where we have taken p is equals to 2, then we are getting our least square. So this is the formula for the least square algorithm. So this is just an expression. So this is the Jacobian matrix and this is our delta x, so this is our deviation matrix, this is our error function, error matrix. So we are, so our aim here is to calculate this deviation matrix, so the delta x. So what this delta x tells us is the difference, like how much the response whichever we are obtaining is getting deviated from the response which we are desired of. So this difference can be calculated using this deviation matrix. So nothing we have done here. So all thing is we have defined the Jacobian matrix. So we are given the J transpose how to do it, and here we are calculating the product of J transpose with J, and then we are calculating the J transpose and E, the multiplication here. Now we are solving the system of equations, so using the Gaussian elimination. So here we are doing a back substitution for getting the delta x, and then when we just implement this code and give the values of this x1 and x2, so we are going to get the value of delta x, so how much it is deviated. So when the values of x1 and x2 are 1, the delta x will be somehow this much, and when it is 1 and 2 we are getting this as a output. So this is about the least square optimization. So thank you for watching this video.